Okay, let's get started. Okay, any questions before I actually head into the content of today's lecture? Any questions? So on the board, I want to remind everybody that next Monday is the time you will be able to reserve your midterm 1 spot. Okay, so make sure you mark your calendar. Make sure you actually reserve your spot as soon as possible. Okay, so let's actually the first things that I want to remind everybody. Second thing is that on the board, I actually summarize all the equations that you will need for chapter 11. Okay, so trying to actually make your life easier, right? Only condense the most important equation that you need is something that I want you to learn too. Okay, so we'll do this for every single chapters. And then next week, we're going to finish chapter 12. And the following week, which is like 1 week before your exam, we're going to have a review section for the whole week. So we're going to go through more questions, okay? And I keep saying the same thing, I keep repeating myself, but I feel like sometimes student doesn't actually understand, okay? So the things that you really need to actually practice a lot for this midterm, for the midterm one is really all the questions we went through, which is actually the real exam questions, okay? Before your real midterm one comes, you will be able to access this so-called practice midterm one, okay? Historically, students say it's actually really very, very similar to what I'm going to see in the real midterm. So make sure you actually do that, okay? Previously, I actually do a analysis, trying to analyze the student who did the practice exam versus the one who didn't do the practice exam. There's such a huge gap between the two. Okay, so trust the statistics. Okay, that's what has been shown in the past. Okay, another thing that I will strongly encourage everybody to do is actually trying to get the old practice exam or old exams from your senior friends. Okay, I know informed by the student. Okay, that the ACS chapter, the things have the old exams. Okay, so if you gather those exams from your friends, great. Okay, but if you don't and they want to actually get those information, then go to the ACS UH chapter. Okay, I think they have those things too. Okay, so the more you do it, I mean, you'll feel a lot more confident when actually walk into the CASA. Okay, and I keep emphasizing that you should actually practice to use your calculator. Okay, and many students actually come to my office. The first question I ask you, okay, where's your calculator? Okay, so I really want you to really practice to use your calculator. All right? Okay, but other than that, any other questions? If not, we'll just go into the contents. Okay, so far, we kind of finished this, and the three main things of chapter 11. Okay, so the first thing we learn is that we start to learn how to write the red laws. Okay, so when we talk about the red law, it's really trying to understand how the reaction rate is related to the reactant concentration to certain order. Okay, and then multiply a rate constant K. Okay, so in your homework, you often got asked about like what is actually the average rate of the reaction or the average rate, average disappearing rate of your reactant or average production rate of your product. Okay, and those things will be calculated using these very simple equations. Okay, one thing I want to point out is that if the question is specific asking you the disappearing rate of your reactant, what it really asks you is actually this term, right? You need to actually need to be able to tell, okay, what the question is asking you. Okay, if it specifically says the disappearing rate of a specific substance, then all you do is actually calculate the concentration change over the time. Okay. However, if it's asking what is the overall reaction rate, okay, it's a reaction rate, not the reactant change rate or product change rate, it's reaction rate. Then you actually further normalize by the coefficient in front of less specific substance. Okay, so let's actually something that you should actually definitely know. Okay, so let's actually what we learned in the first place. Then we start to actually talk about the differential rate law. Okay, for the differential rate law, it always have this form. Okay, the reaction rate is equal to a rate constant K times reactant concentration to certain power. Okay, here we use N to represent the orders. Okay, and the N can only be determined experimentally. Okay, that's actually a time we actually went through these big tables, right? Where all the reaction rate equation based on the numbers. Then you do these equation divisions to figure out the orders. Okay, so that's actually a very important concept that you must know. The reaction rate, okay, the differential rate law will always this form. The rate equals to rate constant K times reactants to certain power. Okay, it will not have the form like rate constant K times product to certain power. They will never appear. Okay, it has to be reactant. Okay, then we start getting interested into how this concentration of the reactant or product change over time. Actually, reactant concentration change over time, right? Therefore, we went to a very simple case where it's actually you only have one reactant. Okay, we name those reactant as A, right? And depending on the order of the reaction, then you have different type integrated rate law. Here, you actually memorize for the zeroth order, first order, second order integrated rate law will look like this, right? Concentration of A at time t equals to KT plus A0. Let's for the zeroth order. Okay. First order will be natural log AT equals negative KT plus natural log A0. Second order, 1 over AT equals to KT plus 1 over A0. Okay, so those are the three equations that you must memorize. Okay, so every time you see a question have the information of time, then you know one of the three will be the equation you must use. Okay, so one thing I did not talk too much about this is actually the T half or the half-life of a reaction. Okay, so you actually don't need to actually memorize too much other equation. If you want to memorize, that's totally fine. Okay, how the rate constant K can be related to your T half. Okay, so that's totally fine. But the derivation is actually very simple. The definition of T half meaning your AT is going to equal to half of your A0. Okay, then to calculate your T half, you just plug in the AT with 1/2 of your A0. And then you solve the T, there will be the T half. Okay, so this is kind of the example that I want to show. Okay, so if you can know the T half, meaning that your AT is going to be the half of your original concentration. Okay, then you just plug in into, or I think I use zeroth order as example, right? You replace your AT with 1/2 of A0 equals to negative KT. Right now the T will become T half. Okay. Then you just move these things around. You move this to the left, move that to the right. Then you have this. Okay. Then you can actually get, sorry, this should be T half equals to 1/2 of A0 divided by your rate constant K. Okay, so that's actually how you actually calculate your T half. Okay, but if you know the definition, you actually doesn't really need to memorize this equation. Okay, so the very last things I want to actually talk about for chapter 11 is actually to introduce the concept of activation energy. Oh, sorry, there's actually one more thing. After that, which is actually a thing we want to talk about a lot today. Okay, elementary steps. Okay, so these are actually things we are going to focus on today. Okay, and after this, then we'll start to talk about the very famous term activation energy. Okay, how that is going to be related to your rate constant K. Okay, so those are the kind of things that will be covered for chapter 11. Okay, so after this quick rundown, let's just refresh our memory. So we're going to do a few questions before we move on. Okay, so the reason I posed this question is because I got asked about this question so many times in the past couple of days. Okay, so we say let's actually, it is very important that you know the unit of K, right? Because from the unit of K, you can actually know the reaction order directly, right? So some of the students actually get confused about how you can actually really calculate the unit of K directly, right? So first of all, the answer of this one is B, okay? But I want to actually show you how, okay? So to actually solve the unit of K, I think you have similar questions in your homework as well, okay? You need to know, we always come back to this very simple thing. Right, so you know that's actually the format you're going to always have when you write out this reaction rate for different orders, right? So in your homework, you are going to see, let's say, I think it's something like this. Okay, so what's the unit of K in this specific expression? Okay, so one thing that you must know is that the rate of a reaction, okay, the unit, you just think about these things in the unit domain. Okay, so you're not actually really talking about specific concentration, but you're actually trying to write out the things in terms of unit. Okay, so what's the unit of rate? The unit of reaction rate will be what? Molarity per second, right? Because when we talk about a reaction, we only care about how its concentration change over time, right? Concentration change over time, translate that into equation is molarity over second. Okay, and then this thing will never change. Every time we talk about the reaction rate, you must have the unit of concentration per second or concentration per minute, right? But concentration per time will be the unit you always going to have for the rate, right? And then you write out your equal sign. Okay. Then on the right hand side, you don't know the unit of your K, so you just put K over there. Right? But do you know the unit of this guy? It's concentration to the first power, right? That means you must have concentration to the first power. Does that make sense? Everybody follow? Okay. How about the second term? What's the unit of this guy? Concentration to the half power, right? That's what you should write. Okay? And then you have this equal sign, right? That means the unit on the left will equals to the unit on the right. Okay, but the unit on the right is actually have three components, right? So the product of the three will give you this. All right? So let's combine these two. Okay, what's the concentration of first power times concentration of second power will give you is concentration to this power, right? So that's actually what you have on the right. Okay, let me just write this in the scientific way. Okay. Does everybody fine with this? Okay, if it doesn't, that means actually you have some mathematical problem. Okay, then come to me. Okay. Every time you have these reciprocal things, you can write it into the -1 power of that variable. Okay. So now you look at this. That means actually the unit of lead times this will give you lead, right? The unit of this multiply lead will give you this. Therefore, you know your K will simply equals to, you divide this terms on both sides. You divide it. Okay. Therefore, you know your K will equals to okay. Then I will put this I'll put these terms outside. Okay, then we look at this. When you divide two numbers will have the same base, then the operation is actually to do subtraction in the orders. Okay. Therefore, you know your K is going to have double the unit of your K. Okay. Does everybody follow this? Yeah, I hope it's actually simple enough that you know. Okay, it is not that difficult. Okay, you just need to be fair. Okay, the unit on the left will always equal unit on the right. And you should know that how to do these simple numerical operations. Okay, so let's get back to the question that we had previously, right? We said we want to know the unit of K for the first order, zeroth order, and second order, right? So for the first order means what? Means you have rate equals to K times first order, right? So concentration to the first order. The unit of your rate is still the same. Unit of K you don't know, but this one is the concentration to the first power, right? Therefore, this and that will cancel out. The K is going to have a unit of per second. Okay? Yeah, so you can actually do the same operation. Then by doing that, you'll be able to get the answer will be your B, right? For the first order, zeroth order, and the second order. Okay, so I hope that actually make this more clear to you. Okay, so you can just do all your homework correctly. Okay, any other questions? Now let's do next one. So this is actually testing you that do you actually memorize the integrated rate law equations? Because the integrated rate law, they are all linear equations. Okay, so for the zeroth order, what do we have? Is AT equals to KT plus A0, right? Therefore, you know, for the zeroth order, you're looking for the concentration term directly, right? So it's actually A over T. So your answer is either A, B, or C. Cannot be D, right? For the first order, then what do we have? Natural log AT equals negative KT plus A natural log A0. Meaning that you have this very clear natural log term to show up. Okay? With that, you will only come to the correct answer, C. Okay? And then for the second order term, it's actually 1 over AT equals to KT plus 1 over A0, right? So you must have actually 1 over AT as your answer. Okay? So those are the things that you must understand and you must memorize, because once you know this, all these questions become very simple. Okay? Let's look at the next one. Oh, this is actually things we're going to talk about now. All right, so get back to here. So what we're going to talk about today is actually the reaction mechanism. Okay. So why do we actually care about the reaction mechanism? Okay, there's actually historical reasons. Okay. So back to like 18th centuries, okay, human encountered the first crisis. Okay, we don't have enough food. Okay, the human population is actually increasing, right? So we don't have enough food. So there's actually a very famous scientist, Dr. Haber. Okay, he's actually the first person who invented the first fertilized ammonia. Okay, and then back to that time, they're trying to figure out, okay, what could be actually the most effective way to produce the ammonia. Okay, therefore they start to actually investigate, okay, how the reaction rate is going to change depending on the initial concentration. Okay, which is actually the things that we write for our differential rate law, right? Rate equals rate constant K times reactant to the certain power. Okay, that's why that thing actually becomes something so important in 18th century. Okay, so once you actually write that out, okay, you can actually determine those things experimentally, no problem, right? But people start to wonder, are there actually any ways we can actually really figure out what's actually happening at the molecular level, right? If we figure out the mechanism, maybe we can actually create some other creative way to make the things go even faster. We can have higher production rate, right? So then back to that time, the scientists start to create something that's very interesting, okay? One thing that human can do is actually, we can always imagine how things happen, okay? Then we can actually specifically say, okay, this thing's going to happen in this very specific way, okay? The beauty of that is because since you hypothesize certain things happen in a specific way, you can actually calculate how the reaction rate, okay, or depending on the reactant concentration. Okay, so you can actually derive a hypothetical rate law for the model that you create. Okay, and then you're going to compare that hypothetical model to the real experimental results. Okay, if it doesn't fit, that means actually your model is not correct. I'm going to create a new one until one day the rate law that I derived hypothetically agree with the experimental one. Okay, and that will be a potential correct model for reality, right? Then what scientists do next is actually, then let's actually fine tune a little bit. Okay, let's fine tune the experimental condition a little bit. Okay, can actually predict experimentally how it's going to evolve, right? So by doing actually a lot of this repetitive process, then that's how we actually gradually, understand how things actually happen at the level we can actually really see it. Okay, it's actually very cool and very smart way to understand this microscopic world. Okay, so what we're going to learn today is actually to tell you, okay, so what is actually the hypothetical red law can be generated from these things, so-called the elementary step. Okay, so here I actually list out the steps. This is actually not the this is actually the way we solve the problem, okay? But I want to actually using the example to show you how these things was done in the past, okay? But before we go into there, you want to make sure that you know every time when we see an equation, chemical reaction, okay, you must identify who are your reactants, who are your products, okay, what are the intermediates, okay, what is the catalyst. Okay, so a lot of things need to be actually identified when we see this, the elementary step mechanisms. Okay, so we'll go through that very soon. Okay, and the basic idea is that if you think about the, you're going to have like multiple steps in your model, right? But there's actually one step. There will be the slowest step. Okay, and that one step will be the step that determine the rate. Okay, so the analogy in our daily life is actually like you actually drive into the IAH airport. Okay, so you take 59, I guess. Okay, so you drive all the way. And then on the 59, you can drive like 60 miles per hour or even faster, right? But we have to enter the airport, especially when the airport is under construction. You want to go to like Terminal D or Terminal C. There'll be actually a long wait over there, right? And that wait will pretty much dictates how much time you need to spend to get to the airport terminal, right? So less specific sections will be your rate limiting step, okay? So when scientists start to propose all these mechanisms, they want to figure out, okay, what is actually the rate limiting step, okay? So all the rate law can be actually write out based on starting from that rate limiting step, okay? But once you write out that rate limiting step, okay, there could be actually a situation that when you write out that rate limiting step, okay, it may actually contains something that doesn't belong to your reactant. Okay, that means actually because the only thing you can determine is actually how the rate is related to the reactant to a certain power experimentally, right? So you need to actually change that. Okay, so you need to actually use this other relationship to actually get all those things become the reactant. Okay, so there will be actually the flow the scientists want us to do. Okay, and then the way you do it is actually start to introduce the term called the KEQ, the equilibrium constant. Okay, I assume everybody know what KEQ is. Maybe not. So you have A plus B give you C plus D. The KEQ only equals to C to the C's power, D to the D's power, A to the A's power, B to the B's power. Okay, so this is actually what we learned when we were actually in the high school when we learned the chemistry. Okay, that's actually how we define the equilibrium constant. Okay, so it's very different from the rate constant, okay, the lowercase k. Okay, for the equilibrium constant, we always use uppercase. Okay, it's capital K EQ. Okay, so we need to actually know this so that we can actually release going from the elementary step, from the rate limiting step to write out our rate laws. Okay, so those are the things, kind of the fundamental things that we need to actually have. Okay, So, with that being said, let's go through a few examples, then you can see these things more clearly. Okay, so in this question, it says, consider the reaction A plus B plus C give you D, which is found to be first order in A, first order in B. Which step in the proposed mechanism must be the slow step in order to agree with this red law? Okay, so every time you see this type of questions, you need to know when we write out the red law, right? It must be equal to rate constant K times to reactant concentration to certain power, right? So if you look at this equation, A plus B plus C give you D, what are the reactants? A, B, and C, right? That means your red law will look something like this. A to the X power, B to the Y's power, and C to the Z's power, right? So let's count the general formula you're going to have before you even get started, okay? So what's the value you can have for your X, Y, and Z? Yeah, I know X is 1, right? But what's the range? If you don't see that, okay, if you just look at the general form, okay, the X, Y, and Z, it can vary from 0 to any numbers. Okay? So why do I emphasize this? So your X, Y, and Z can be belongs to any number, any past 0 to any number. Okay? The reason I bring this up is because I want you to see if your X equals to 0, Y equals to 1, Z equals to 2, then what do you rate? What do you have? Will be rate equals to K times what? A to the zeroth power, right? What's the value of A to the zeroth power? 1, right? Therefore, you know it will be this. Okay? And then B to the first power, right? And then C to the second power. Okay? I want to focus on the things I just wrote. Okay, the red law. What's the things that show up inside the red law? Does it contain A, B, C, all three? It doesn't, right? So you don't need to actually contain every single reactant to give you the valid red law. Okay? But you can only have reactants. You cannot have product inside your red law. Is that clear? Everybody follow what I say? Okay. Good. Now we can actually really start to reread our questions. Okay. So the question is actually asking you what? Which step is actually the slowest step, right? So let's actually asking you which one is actually the rate limiting step. Okay, so you have 3 steps here. Okay, so it asks you which one is actually slowest one. Okay, all right. And then we also know, if you read the question again, you know the experimental rate law is the rate equals rate constant K times A to the first power, B to the first power. How about C? Do you have C information here? You don't, right? That means what? The order for your C is 0. Okay? It did not say it, but you need to know it. Okay? So you should know that the C is actually 0th order. Okay? And then it says, okay, you have 3 steps. Step 1, step 2, and 3. The one is A plus B give you X. The second one is X plus C give you Y. The third one is actually Y give you D. Okay. So the beauty of this step 1, 2, and 3 is so-called the elementary step. That means that reaction will actually happen just like what you write here. Okay, so let's actually know further underlying things going on. No, for the elementary step, the beauty of that is actually the things will actually happen like how you wrote it. Okay, if you have 1A, 1B, that's going to form X. That means actually 1A, 1B, they're going to form X. Okay, that means actually rate is actually going to be proportional first order of A, first order of B. Okay, and they will give you X. Okay, so let's start from this. Let's say if this is actually a rate limiting step, okay, then you are going to write the rate equals to rate constant K times your Y. Okay, because Y is actually reactant for this specific reaction, for this specific step. Okay, and then the Y is not just Y, it's actually Y to the first power because the coefficient is just 1. Okay, you can only do this when you have elementary step. Okay. All right, so let's actually the first thing you see. Then you see this. The rate is going to equals rate constant K times your Y. Okay, then you need to think about this. How does this compare to the experimental one? They are not the same, right? Because the experimental one is actually K times A times B. But the one right now you get this one is K times Y. Okay, so what is Y? Is Y a reactant? Is Y a reactant? It is not a reaction, right? What is Y? Is it a product? It is an intermediate. How do you know it's an intermediate? Okay, so one thing that you also need to know is that it's very important, okay? You propose this elementary step, okay? If you add up all the elementary steps, you will go back to your original chemical reactions. Okay, so if you add them up, you will see that X, they're going to cancel out, right? Y, they are going to cancel out. Therefore, if you add the 3 steps out, you got A plus B plus C, they give you D, which is the given equation. Okay, that's actually another important feature for this elementary step. When you add up all the steps, you need to actually go back to the given specified chemical reactions. Okay, if it's not, then you did not actually propose a reasonable elementary step. Okay. Next things. From here, I guess nobody will have problem with to identify who is actually your reactants. Okay, A and B and C are your reactant. D is your product, right? And then how about X and Y? X and Y is called the intermediates, right? That means actually they were formed during the reaction. Okay, but you will also be concerned within the reactions. Okay, so on the surface, they look like they never actually exist. Okay, but they do. They just exist in a transient amount of time. Okay, so you need to know the X and Y. They are so-called the intermediate. Okay? Any questions for this? Everybody follow this, right? Let's say another very important thing is called a catalyst. Okay, so how do you know you have a catalyst if you have multiple elementary steps? So catalyst is actually another thing that doesn't show up in your equations, right? That means it will actually disappear once you actually add up all the steps. Okay, so typically you're going to see this. Okay, I'm going to erase the Z afterwards, okay? But just to show you how do you know you have a catalyst. Okay, if you look at these three steps, the Z first appear on the reactant side, right? Of course, the Z will cancel out afterwards. Therefore, you know it will either be the intermediate or the catalyst, right? The difference between the two is actually that the intermediate has to be formed. Therefore, the first appearance of intermediate will be on the product side. Catalyst is actually a different story, right? Catalyst is actually you add in already. So it presents inside your equation, okay, originally. Therefore, it will first appear on the reactant side. Okay? So that's actually how you tell whether you have a catalyst or you have a intermediate. Okay? I believe that your homework and quiz will actually test you something like this. Okay, so you must know how to tell what you have is reactant, product, intermediate, or catalyst. Right? All right, so get back to here. Okay, I can erase this now. So if this is actually your rate limiting step, then you know the equation that you get right away, that doesn't agree with your rate law, right? So how about others? If this is actually your rate limiting step, you're going to have rate equal to K times X times C, right? Is X your reactant? Yes, right? But X is not your reactant, right? C is your reactant, but X is not, right? So not very clear. Okay, how about this guy? You got the rate equals to K times A times B, right? Does this actually match with your experimental determining one? Yes, right? Then that will be actually the step you're actually looking for. Okay, is this clear? Yeah, so it's actually, once you know the principle, then it's actually very simple, right? So just looking for the equations that can actually match the experimental determining rate law. Okay, so this is actually the simplest case. Okay, so we're going to use the next question to tell you, okay, what if it doesn't look like that in the beginning? Then what do you do? Okay, so any question for this one though? The answer is the first one. Okay, so this guy is the rate limiting step. Okay. Let's look at these questions. This says for the reactions NO2 plus CO, they give you NO plus CO2 at the temperature below 500 K. The rate law is rate equals to K times NO2 to the second power. Which mechanism is consistent with this information? Okay, then it gives you two mechanisms, and one of them is actually right. Okay, so Q is, you want to know is mechanism 1 or mechanism 2. Data that you have is for the mechanism 1, NO2 plus NO2 give you NO3 plus NO. CO plus NO3 like give you CO2 plus NO2. Okay, so mechanism 1 says this is actually slow. Mechanism 2 says that it's actually slow. Right, so those are the information that you get. And then the experimental rate law will have rate equals to rate constant K times NO2 to the second power. Okay, so you need to actually pick, okay, is this correct or that correct? So that you can match this, right? And the way you write out the rate law is always you start from the slowest step. Okay, so that means actually if you have mechanism 1, okay, so the mechanism 1, then you know your rate law will equals to rate constant K times this is actually your slow step, right? Therefore, you're going to write that directly. So you have NO2 times your NO2 that equals to K times NO2 to the second power. Okay. For your mechanism 2, then you start using this guy, right? The slow step. Then you know your rate is going to equal to rate constant K times CO times NO3. Okay. So for mechanism 1, you have this. Mechanism 2, you have that. Then start to compare the one to the experimental ones. Okay, which one agree with the experimental one? This one, right? Therefore, you know mechanism 1 is the correct mechanism. All right, very simple, right? There's actually not much to say actually, because once you know, okay, you always need to actually looking for the relative step, okay, and then the rate law you got from the relative step. If they agree with the experimental one, then it's a correct answer. All right, any questions for this? Yes, we will go through that. Okay, so every time when we propose this elementary step, like A become B, B become C, C become D, right? So what does that mean? Even though I say A become B, okay, in reality it is bidirectional things, right? So you have the forward rate and the reverse rate. Okay, so when you have a fast step means actually it prefer going from one direction to the other. Okay, what's actually the slow means? Slow means actually you go forward slow, go reverse is slow too. Okay, so you can think about this way. Okay. Now I want to think about this. Okay, let's say A to B and then C to D, they are really fast. Okay, so if this is actually true, okay, B and C will be your local red trap. Okay, because A can easily become B, right? So they will actually always doing this really fast. Okay, And once you go from B to C, and C can go to D, right? So C and D will doing the same thing. Okay, so who is actually the one that's very slow is actually B to C. Okay, and because your A to B and C and D and C to D, that is actually really fast, right? So the end result is actually the B and C concentration counts reach a steady state. They don't really change. Okay, therefore it kind of look like a equilibrium status. Okay, so that's why later on we're going to tell you, okay, how the equilibrium constant KEQ will get into play when we write out the red law. It doesn't give you the reactant directly. Okay, yeah, but let's count the fundamental pictures that you should actually have. Okay, so let's get back to this. This is actually the time that things get a little bit more interesting and more complicated. Okay, so this question says, the proposed mechanism for a reaction ClO minus plus I minus become IO minus plus CO minus. And then they figure out the mechanism. Okay, so these three are the elementary steps. Okay, so you have step 1, step 2, and step 3, where the step 3 is actually the slowest step. Okay, so it asks you, what will be the red law for this specific reaction? Okay, so how to actually go from here? First, you want to make sure that you know what are your reactants, right? So what's the reactant? This 2 is actually your reactant, right? So you know the final form of your red law will look like what? It will look like rate equals to rate constant K times ClO minus 2x power I minus 2y's power, right? So that's the kind of format you're going to have. Okay, but the value of x and y can vary from 0 to any numbers. Okay. Then what you do is actually you start from the slowest step. Okay, so from the slowest step, you know. Sorry, I forgot my QD pad. Q is actually the red law, right? D is all the things. Okay. So the plan is actually you start from the slow step. Therefore, you can write the rate is going to equals to rate constant K times OH minus times HIO. Okay, so this will be the first thing you do. Once you actually write these things out, you'll realize that the red law that you got doesn't contain the reactant only, right? So what is your OH minus? OH minus is a intermediate, right? How about your HIO? HIO is also a intermediate. Is that right? Yes, it's also intermediate, right? So then you know both things you got is intermediate. Therefore, you need to actually do some more work to convert that into the form that match your experimental results, right? And the way you do that is actually using the equilibrium constant K. Okay, so let's do this first. So you're going to substitute these two to become your reactants. Using KEQ. Okay, so what are the things that you can use KEQ is actually using the fast step. Okay, so let's start from the first term, OH minus. Which equation has the OH minus? The first equation, right? The first step you have that. That's actually a fast step, right? Therefore, you know the first equation is ClO minus plus H2O That become HClO plus OH minus. For this specific equation, you can write a KEQ1, which is going to equals to HClO concentration times OH minus concentration divided by ClO minus. Okay. So that's actually the first thing you do. Okay. Everybody have question with this? Everybody notice that I did not write the H2O? Okay, what's the reason for that? Yeah, so for the pure liquid and pure solid, it doesn't go into your equilibrium constant. Okay, so H2O is actually a pure liquid, so it doesn't go into your equilibrium constant. Okay, so make sure you actually know that. Okay. So once you have this, then you can actually rewrite the things as you can actually express your OH minus. Okay, so your OH minus will equals to your KEQ1 times ClO minus divided by your HClO. Okay, so we're going to use this. Okay, so you kind of like using the KEQ equation, rearrange it so you can actually express the OH terms with this guy. Okay. Once we finish this, then we move to the next one. Next one is HIO, right? Therefore, we're going to use the second equation, I minus plus HClO. That becoming HIO plus Cl minus. You can write out your KEQ2 is going to equals to HIO first power times Cl minus first power I minus times HClO. Okay. So the things that you want to actually use is this, right? You want to actually know how you can actually express your HIO in terms of other terms. Therefore, you know, you can actually go from here to write out your HIO can be written as KEQ2 times I minus times HClO divided by Cl minus. Okay. Therefore, we're going to replace the HIO with this term, OH minus with that term. Okay. Therefore, you can actually rewrite this rate. It's going to equals to rate constant K times OH minus will equals to KEQ1 times ClO minus HClO. HIO will equals to KEQ2 times I minus HClO Cl minus. Okay. Then you will see that this and that will cancel out. Therefore, you know it can be rewritten as K times KEQ1 times KEQ2 times ClO minus times I minus divided by Cl minus. Okay, so you end up with this. Okay, everybody follow this? Okay, so what you will do next is actually These three terms, they are just constant. Okay, so K, KEQ, they are all constant. One is actually rate constant, one is actually equilibrium constant, right? So here, maybe I should actually label with K1. Oh, this is actually which step? The third step, right? Maybe I should put K3, right? To indicate is the third step. The third step of my elementary step. Okay, so this will be K3 times your KEQ1 times your KEQ2, right? So the product of the three will actually equals to the final rate constant K that you are going to have. Okay, and then you end up with this will be CLO minus to the first power times I minus the first power, and then CL minus to the -1 power. Okay, so this is actually the derivation you're going to go through. Okay, so if you look at this, the red law have a form that contains reactants, right? So CLO minus is actually your reactant. The I minus is your reactant. Okay, and it's all to the first power. Okay, so everything actually looks fine. But for this one, you still have what? Cl minus in your final red law, right? You still have Cl minus in your final red law. And when you go back to look at this, what's your Cl minus? Cl minus is actually your product. Okay? So what does this mean? So this means actually it doesn't really actually agree with your experimental results. Okay. Okay. So what it means is actually if this is actually what you propose, okay, then you should see this product is going to influence your reaction rate. Okay. But when you do the experiment, you know that's not the case. Okay. When you do the real experiment, it's not the case. Therefore, you can come to a conclusion that the proposed mechanism is not the final mechanism that you can use. Okay, but the derivation step is always the same. You start from the slow step. You write out the red law based on last step. Okay, and then if the species you have from last step doesn't belong to your reactants, then you start to looking for the fast step and then replace that reactant using your equilibrium constant. Okay, so if everything is actually right, then you actually get back to the red law that agree with your experimental ones. Okay, and that's actually how the scientists figure out the mechanism, even though we cannot really see how the molecule interact with each other back to 18th centuries. Okay, so this is kind of the things that we will need to learn. Okay, students typically actually get very confused here. Okay, but I think this is because that we need to actually have a clear distinction about this hypothetical red law and the experimental red law. The difference needs to be actually very clear. And then we need to actually also get ourselves familiar with how we can actually go from a hypothetical mechanism to derive the corresponding hypothetical red law so that you can actually compare to the experimental one. Okay, I hope that makes sense to everybody. Yeah, but it's pretty much the contents they want to know for the elementary steps. Okay, any questions? Everybody fine with this? Okay. The very last thing we want to talk about today, which is actually the very last one of this chapter 11. Okay, so it's actually this very famous Arrhenius equation. Okay, so this is actually equation. So if you look at this equation, on the left is your rate constant K. Okay, and on the right, you see the first thing is actually the A. Okay, we call this frequency factor. Okay, EA is the activation energy. R is just a constant. T is just temperature, okay? So how does this actually tell us? Okay, so this actually go back down to the very fundamental pictures, okay? For the reaction to occur, okay, let's say you have substance A, substance B, okay, they're going to form a product C, okay? What's the first thing they need to do? They need to meet each other, right? So you see the prefactor A is actually to describe how frequent they're going to encounter with each other based on the concentration. Okay? And then there's actually a second term, which is the exponential negative EA over RT, right? So what does that mean? Okay, it actually describes how many of the molecules have enough energy. The energy is actually larger than the activation energy. Okay, so for the reaction to occur, first, of course, you need to meet, right? But not just meet, okay, there's just something else that's important, is that are you actually energetic enough to produce the product, right? So you want to actually have idea about like how many of these collisions, that among these collisions, how many of them is energetic enough, right? And when we say energetic enough, it's actually, it must have the energy higher than your activation energy, okay? So that's why you have this EA term inside that exponential term, okay? Then the next thing is actually, how do we actually define the energy of a molecule? It depending on the temperature. Okay, so you guys already did some chemical reactions, right? You guys have the chemical lab. Okay, so what's the things you do the most? You cook. You heat up things, right? So what does that change? It's change of T. Okay, so what does that mean? It's actually when you heat up your solution, what you really do is actually you give more energy to those molecules. So you produce a higher population of activated molecule. Okay, so that when they actually encounter, then they can actually form the product. Okay, so that's the meaning of the equation. Okay, so the reaction rate constant K, okay, is related to two factors, right? One is actually how frequent they collect. That's actually the frequency factor. Okay, second is actually among these guys who collect, how many of them is actually energetic enough, right? So they use the ratio, right? So I have that much to hit, that's energy level I need to get. Okay, then depending on how much energy I got from my environment, then it actually dictates the populations. They can actually make these things to happen. So let's take a physical meanings of that equation. It's actually very simple. Okay, so if you have that concept in mind, it's really two terms. One is actually frequency factor. The other is actually the population of the high energy molecules. And then mathematically, it translates into this exponential term. Okay, e to the negative EA over RT. Okay, so let's actually how the rate constant K is related to your activation energy EA and the temperature. Okay, so this is actually one of the most famous equation in 18th century. Okay, so there's like so many scientists trying to actually give us this golden equation. Okay, so inside chapter 11, there's actually one type of question you're going to encounter a lot is actually how this reaction rate constant K change with different temperature. Okay, so openly we actually rewrite this equation into in the natural log form. Okay, so these two, they're actually equivalent. So the things that I do is actually I take natural log on both sides. Okay, so your left-hand side becomes natural log K, and on the right-hand side becomes natural log K, and then you bring out that the exponents, okay, EA over negative EA over T, okay, out. Okay, so these two is actually equivalent. Okay. So one type of question you're going to see a lot inside this chapter is that, okay, if I tell you the reactant content is actually K1 at the temperature T1, if right now I change the temperature to T2, what will be the K2? Okay, so those are the typical questions you're going to see when we want to use this specific equation. Okay, so what you do is actually you write out like natural K1 equals to lna negative EA over RT1, and then do the same for the T2. Okay, and then you can actually compare the two. But the equation you need to actually memorize is this. This is actually a summarized equation, okay, for that specific purpose. Okay. So this equation, natural K2 over K1 will equal to EA over R, parenthesis 1 over T2 minus 1 over T1. Okay, make sure you don't mess up with the order, okay, so they can actually get the correct answer. Okay. So I don't think we'll have enough time to go through the example. We'll go through the example next time, okay? But the very last thing I want to bring up is this. Okay. So go back to this 18th century, okay? That's actually when the inorganic chemistry become very popular. Okay, so back to 18th centuries, because we are so eager to figure out what's the best way to speed up the reaction, right? And then this actually triggers the invention of catalyst. Okay, so what catalysts do is actually, it doesn't actually participate as a reactant, okay? What it does is actually it lower down the activation energy. Okay, so that's actually a key thing because there's a question is going to test you what does catalyst do, okay? And they're going to give you many different kind of answer, but all the answer is wrong. The only answer and only one answer that you need to choose is activation energy. Okay, so one commonly seen misleading answer is if you add in the catalyst, okay, you are going to generate more product. And that is actually a wrong statement. Okay, it doesn't generate more product, it doesn't change the equilibrium. Okay, it just makes these things happen faster. Okay, so it won't change the overall population ratio between your reactant product. However, you will let the ratio be reached much sooner. And the only reason for that is because it only changed the activation energy. Okay, so we'll stop here and we'll continue for the example next week.